Hello all. So we are done with the most awaited examination of this year, JEE Advanced. Here we will be doing a detailed analysis of the question papers. So today I will be discussing about chemistry, paper 1 of the JEE Advanced 2024. Okay, so let's move on to the question paper. So this is paper 1 of chemistry. So the first question was related to states of matter, one of the deleted chapters, and you have learned it in physics also. So the first one was related to RMS velocities of ideal gases, right? So a closed vessel contains 10 gram of an ideal gas X, that is at 300 Kelvin, and it exerts 2 atm pressure. And same temperature, we have added one more gas called as Y, and 80 gram of Y is added. Okay, and now the total pressure is 6 atm. Okay, if total pressure is 6 atm, keeping temperature and volume same, partial pressure of Y will be 4 atm. Okay, 2 atm of X and 4 atm of Y, making it total 6 atm. So the ratio of root mean square velocities of X and Y we have to find out. And we know that RMS speed of ideal gas is inversely proportional to square root of molar mass, right? Temperature is fixed. Therefore, if temperature is also variable, root of T by M. Okay, so here we can take this simple relationship, inverse relation with square root of molar mass, right? And we know for ideal gas PV is equal to nRT, and N we can do small m by capital M, okay, given mass by molar mass. So we need to convert this capital M in terms of the given variables, right? So from there we can write capital M is equal to small m RT by PV. Okay, so molar mass of an ideal gas can be written in this formula, mRT by PV. And you know that here for the two gases, R is already a constant, temperature is a constant, and volume of the vessel is fixed. Okay, both are present in same vessel. So this term, if we take a fraction over there, that will cancel out. Okay, so let's see what is the required final fraction. We need RMS velocity ratio of X and Y. So X in numerator and Y in denominator. So that will be simply root of molar mass of Y by molar mass of X, isn't it? So that ratio now becomes root of My by Py into Px by Mx. All others will cancel out. Okay, those are same for both gases. So now let's plug in values for M and P. M is 10 for first gas and 80 for second gas. So here we will be writing root of 80 grams of Y divided by 2 atm pressure. Yes, gas Y is at 4 atm pressure, right? So 4 atm pressure. Now into pressure of first gas was given as 2 atm and divided by its mass was 10 grams. Okay, so that simple relation we will get. And on solving, you will find this is root 4, which is 2, and the ratio will be just 2:1, right? 2:1 will be the final answer. So it is option D, right? So it was a simple one. Now let's move on to the next one. Next one was from P block, properties of P block compounds, right? And it was nitrous acid disproportionation. That is very direct. Nitrous acid disproportionates to nitric acid, which is an oxidized product, and nitric oxide also. So these are the characteristic products. Along with that, H2O is also formed. Okay, H2O is also formed. This is happening in aqueous medium. So HNO3 we could write like, being a strong electrolyte, we can write it H3O plus and NO3 minus and NO gas. So these are the products of disproportionation of nitrous acid. So we can pick option A for this question. Okay, now let's look at the next one. That was related to everyday life, chemistry or biomolecules, a combination of both. But effectively it is checking stereochemistry, right? Okay, so they are giving some information. Aspartame is an artificial sweetener, we know. And it is a dipeptide, okay? It's a dipeptide. And dipeptide's name is also given to us, aspartyl phenylalanine methyl ester. So in this, on left side, that is on N terminus, Okay, N terminus we have aspartic acid, and on C terminus we have phenylalanine. That is the nomenclature of dipeptide. Okay, on N terminus we have aspartic acid, and on C terminus we have phenylalanine. Right. So phenylalanine is present in form of a methyl ester. That means COOH group of phenylalanine is esterified with methanol. So in place of H we have Me or methyl group, which is called as phenylalanine methyl ester. Okay, now let's combine both these through a peptide bond. Okay, that is nothing but an amide bond. So on left side we will have this particular unit, NH2, then COOH, and then it is forming an amide bond with the elimination of an H2 molecule. This OH along with one of these hydrogens will be eliminated in the form of water and results in CONH unit. Right, CONH unit. And if you are drawing that bond towards upside, then of course we can write a wedge over there for the benzyl group, right? And here COOMe. And if you are drawing the bond between carbon and nitrogen towards down, okay, that is all about drawing. So if you are drawing same thing towards down, that is a conventional way, right, zigzag manner. So if you are drawing this bond towards down, then you know that this benzyl group will be on a dashed notation only, that way, right? So that will be our final structure of aspartame. So let's find out the options. The correct one, that will be option B, right? So that is the correct structure for the mentioned esterified dipeptide. Okay, now next one was from coordination compounds isomerism. You know that in our syllabus regarding coordination compounds we have two isomers specifically mentioned. Those are geometrical and ionization isomers. So let's find the correct answer for this question also. So they are saying us to identify the option where set 1, both the compounds of set 1 can show geometrical isomerism. Geometrical isomerism could be either cis-trans isomerism or like facial meridional isomerism. Okay, one of those isomerism is shown by both the complexes of set 1 and the second set. They are ionization isomers of each other, right? So let's move on to the first option. First one, NiCO4 is given, that is tetrahedral in geometry, so it cannot show geometrical isomerism at all. So no need to look into option A then. Then if you go to option B, COEN NH3 twice Cl2, it can show geometrical isomerism. It is an octahedral complex. PDCl2 PPH, that is a trigonal, that is a square planar complex, so it can also show geometrical isomerism, cis-trans isomerism. So both are able to show geometrical isomerism. Now if we go to second set, then we will find that they are coordination isomers. They are not ionization isomers. They are coordination isomers of both each other, right? So this is also not an answer for us. Now moving on to option C, there we will find Ma3B3 type octahedral compound which can show facial meridional isomerism. So this can show geometrical isomerism. This is also able to show simple cis-trans isomerism. So set 1 is okay for us. Then set 2, if you look, then yeah, clearly it is a ionization isomer. Here we have SO4 outside, chloride inside. There we have chloride outside, sulfate inside. So that is clearly ionization isomers. So say option C will be our right choice for this fourth question. Okay, now, so that was the first section of the question paper, paper 1. Single correct answer type questions were there, 4 were there. Now, fifth onwards, we have section 2, that is multiple correct. One or more options will be correct here, right? So let's see what are those questions. Okay, first one was from structure of atom. We need to identify correct statements regarding atomic structure. First one is uncertainty principle rules out the existence of definite paths for electrons. Yeah, that is true. So that is a decline of Bohr model, right? We know in Bohr model everything is very definite. Electron has definite radius of orbit, then definite energy, definite velocity, etc. All are definite. for Bohr model of atoms, right? And that is just nullified by the two concepts, that is de Broglie concept and uncertainty principle, right? So we are sure that uncertainty principle clearly rules out existence of definite paths or so-called orbits for electrons. For after uncertainty principle, we don't have orbits, we have orbitals. Okay, yes. So A is a true statement. So we cannot have exact values of position and velocity or position and velocity or position and momentum for an electron, right? For any object, and it is particularly significant for electrons, microscopic objects like electrons. So that is true. Now, energy of an electron in 2s orbital of an atom is lower than energy of an electron that is infinitely far away. Okay, that is also true. If the electron is closer to nucleus, positively charged nucleus, that will be more stabilized than an infinitely far electron, right? So that is true. We can verify this with the help of our simple energy equation given by Bohr model is equal to minus 13.6 z square by n square. So more negative energy means lower energy. Okay, less negative means higher energy. So if we put lower values of n, then this will give us more negative value, or if we increase the value of n, the value will become less and less negative, right? So that confirms 2s orbital or closer distance to nucleus will have lower energy than a farther electron. So this is also a true statement for us. Okay, now again they are saying according to Bohr model, most negative energy value for an electron is given by n is equal to 1. That is true. What is the minimum possible value of n, principal Quantum number? So that is the most negative energy value possible in a hydrogenic species. So according to Bohr model, most negative, that is the highest negative value for an electron, and which corresponds to the most stable orbit. That is also true. Most negative means very low, lowest energy means the stablest orbit. So C is completely true. And then last they are saying, according to Bohr model, magnitude of velocity increases with increase in value of n. That is a wrong statement. We know that V is proportional to Z by n. Okay, this way you can easily derive also, right? So according to Bohr model, magnitude of velocity decreases only with increase in values of n, right? So A, B, C are the true statements for us. Okay, now next one from multiple correct section is from organic. Okay, the very familiar reaction of isopropyl benzene or cumene, right? That is cumene hydroperoxide process for phenol synthesis. So reaction of isopropyl benzene with oxygen followed by treatment with dilute acids forms phenol and a byproduct P. Okay, so we are very clear that byproduct P is going to be acetone. Phenol and acetone are the products of hydroperoxide rearrangement after oxidation of cumene. So reaction of P we are doing now, reaction of acetone we are doing now. Acetone on treating with 3 equivalents of chlorine gives a compound called Q. So that would be CH3CO CCl3, right? So 3 equivalents chlorines will give us a trichloro product. So it is a substitution reaction. Now after that, let's call it Q, that is called as Q. So we got P, we got Q also. Now treatment of Q, we are continuing with Q. Q on treatment with calcium hydroxide. Okay, let's say in general if it is treated with dilute alkali solution, then that will be giving us CH3CO O minus acetate ion and CCl3 minus, which is finally obtained as chloroform, right? You know that CCl3 group is a very good leaving group. Okay, so it is a leaving group. So the leaving group leaves followed by OH minus attacks, chloroform forms. So that is a product of hydroxide attack on this trichloro product, right? So it is a characteristic reaction of carbonyl group, addition substitution addition elimination reaction. Okay, now since we are using calcium hydroxide, COH twice is the OH minus donors, therefore we are going to get calcium acetate. If we are doing a sodium hydroxide reaction, we will be getting sodium acetate, right? Okay, now, so we got next set of products. Let's see what is the name given to them. Q with calcium hydroxide produce R and calcium saltase. So this is called as S and chloroform is called as R. Okay, so we are done with the reactions. Now let's go to the options and find out correct statements. So regarding P, Q, R and S. Reaction of P with R in presence of KOH followed by acidification gives this particular compound. Let's check. P was acetone. Okay, so P is treated with R. R is chloroform. So chloroform in alkaline medium, right? So you know chloroform in alkaline chloroform hydrogen is considerably acidic. It's as acidic as water. So that will be generated, and this is now acting as a nucleophile, and this can do addition on ketone. So that will be giving us CH3 COH and CH3 CCl3. A tetrahedral compound is produced. So they are giving the correct structure also, CH3 COH CCl3 CH3. So that is a true statement. That is a nucleophilic addition reaction. And this is a famous drug synthesis also. Okay, you may know the name of this drug. Now going to next option, reaction of R with oxygen in presence of light gives phosgene gas. Okay, a well known fact. R was chloroform, and we know from haloalkanes chapter that chloroform on slow oxidation with air in presence of light will form phosgene, COCl2. So that is a true statement. Now Q reacts with aqueous NaOH to produce, okay, Q reacts with aqueous NaOH to produce that particular alcohol and carboxylate. No, that we have already mentioned. If we are using sodium hydroxide, then corresponding chloroform, corresponding carboxylate salt and chloroform will be the products, right? Because you know this is a good leaving group. Okay, so that will be the product then. Now, so they are talking about Cannizzaro reaction, right? These are the characteristic Cannizzaro products. So we are sure that this cannot show Cannizzaro reaction, right? So that is a wrong statement. Now, S on heating gives P. What is S? S is calcium carboxylate, calcium acetate. So calcium acetate on heating, we know dry distillation of calcium salts. Okay, it's a method to prepare ketones. So calcium acetate, if heated or on dry distillation, okay, this compound on dry distillation, we will be getting CH3, CO, CH3 and calcium carbonate byproducts. So if you look into the nature of the reaction, you can easily convert the given carboxylate salt into products by this particular technique. Okay, CH3CO CH3 and CaCO3 will be formed at the end. So that is a standard preparation method for ketones and aldehyde also. So that is a true statement. P was acetone, we know P was acetone. So calcium acetate on dry distillation or heating will give us acetone as the product. So D is also correct. So A, B and D are the true statements for this question. Now moving ahead, we have a simple question related to chemical bonding, the very famous octet rule. We need to find option where at least 3, okay, at least 3 follow octet rule. Now let's go to the first option, carbon dioxide. Here we know carbon dioxide follow octet rule. It is evident from the structure. Carbon has 8 electrons in its valence shell after bonding. Oxygen has 8 electrons in its valence shell after bonding. C2H4, that is also octet compound. Hydrogen, you know, hydrogen needs duplet only. That is also treated as octet. So NO is a single electron species, which is an exception to octet rule. HCl, hydrogen, chlorine, they have their corresponding noble gas configuration. So it also follows octet rule. So 3 of them follow octet rule. So we can pick option A. Now in option B, NO2 is again an odd electron species, Therefore, not following octet rule. Ozone follows octet rule, which is evident from its structure. You can always draw Lewis structure and verify whether the species follows octet rule or not. So, all three oxygens have octet configuration after compound formation or molecule formation. So, this is a following octet rule HCl we have already mentioned. H2SO4 is an exception to the octet rule. It has 12 electrons in its valence shell after bonding, right? So, it's an expanded octet compound. Okay, so it's an exception to octet rule. Now, in option 3, we have BCl3, which is an electron deficient. These two are single electron species, odd electron, not single, odd electron species. H2SO4 is again expanded octet. So, none of them is following octet rule. Now, in last option, CO2 follows octet rule, BCl3 does not follow, ozone follows, C2H4 follows. So, we can pick option D also. So, A and D will be the correct choices for this particular question. Okay. So, that was one or more than one correct answer type questions. We had 3 such questions, right? Now, 8th question onwards, we have next section, that is non-negative integer type questions. And here we don't have negative scores, right? No negative marking in this particular section. So, of course, you would have all tried all the questions confidently. Now, the first one was from thermodynamics. Okay, we need to find out enthalpy change for X, Y, Z process. Graph is given, volume temperature graph is given to us, right? So, let's look into the process, the nature of process X to Y and Y to Z. 5 moles of ideal gas is taken. Okay, so value of N is 5 and the gas is ideal monatomic gas. Considering only PV work is involved, okay, total change in enthalpy in joules for transformation of X to Y to Z is how much? In joules we need to find out. Data is given, molar heat capacity at constant volume, right? At constant volume is given CVM, that is 12 joule per Kelvin per mole, and gas constant's value is also given as 8.3 joule per Kelvin per mole. So, all we need to do is just find out the correct equation and substitute the values, right? So, let's start with the process X to Y first, that is the first step. X to Y is clearly an isothermal process that is done at 335 Kelvin. So, isothermal process, you know, delta H will be 0 for ideal gas. Okay, enthalpy change, internal energy change, there will be 0 for isothermal expansion work of ideal gas, right? Now, so we are done with first part. Now, Y to Z, if we check, that is an isochoric process, okay, that is done at constant volume. So, their temperature and pressure are varying, okay. So, that is isochoric process and we can apply the general equation for enthalpy of an ideal gas, that is N Cp delta T, okay. So, NCP delta T equation we can use to find out enthalpy change of this process Y to Z. So, what is the value of N? N is 5. Now, what is the value of molar heat capacity at constant pressure? Cv is given for us. So, we know Cp minus Cv is going to be Nr, and for 1 mole Cp minus Cv will be R, and therefore, Cp will be this plus that, Cv plus R, right, 20.3. So, 20.3 joule per Kelvin per mole. Joule per Kelvin per mole, right. So, 12 plus 8.3, that is a Cp value. Now, delta T, temperature change. So, temperature change, this is the temperature change for Y to Z process and that is 80 kelvins, right. So, 80 K is the delta T for YZ process. So, if we look into the units, mole cancels, Kelvin cancels, finally, we will be getting a simple answer in joule directly, right, and that will be 8120 joules. So, that is our non-negative integer answer 8120 in joules. If it was in kilojoules, yes, 8 would be our answer, integer, right. So here 8120 we can write. So that was question number 8 from thermodynamics regarding enthalpy of expansion process of an ideal gas. We got the answer. Now next one is from kinetics. Okay, kinetics, we are given with mechanism of a complex reaction. These are the elementary steps involved in this complex reaction. We need to find overall order of this particular reaction. Okay, overall order of reaction means in terms of its original reactants. So now let's quickly go to the slowest step of the reaction, which will give us the rate law. Okay, the initial step of rate law. So slowest step is step 2 in this reaction, and its rate law we can write like, for that elementary step we can write rate is equal to its constant K2 into N2O2 raised to 1 and into concentration of hydrogen raised to 1, right. So that is the rate law for second step. Now we need to get rid of N2O2, which is not an original reactant, right. That is just an intermediate only. So we need to get rid of intermediate from this expression, then we will be getting the correct overall order of the reaction in terms of original reactants. So N2O2, how we can get rid of that? So for that, if we look into the nearby equations, the steps, we will find that the first step was a fast equilibrium, which is producing N2O2. So that is an equilibrium process, right, fast equilibrium process. So there we can take equilibrium approximation. Okay, equilibrium, you know, rate of forward reaction is equal to rate of reverse reaction, and both are elementary reaction because it's the elementary step of complex reaction, right. So rate of forward reaction is given by K1 into NO square, and rate of reverse reaction is given by K minus 1 into N2O2. So those are equal. That is called equilibrium approximation, right. So we can apply that. So for the first equilibrium, we can simply write K1 into concentration of NO square, which is equal to K minus 1 into N2O2 power 1. That is rate of reverse reaction. Forward reaction rate is equal to reverse reaction rate. Now from here we can get a simple expression for concentration of N2O2 intermediate in terms of our original reactant NO, right. So that is K1 by K minus 1 into NO square. So let's plug this expression in place of N2O2 in that. Okay, so from there we'll get K2 into K1 by K minus 1 into NO square into hydrogen. So that is the final rate law for our reaction. So this is the effective rate constant, let's call it K dash. So rate of that reaction is equal to some K dash into NO square into H2 power 1. So overall rate order of this reaction will be 2 plus 1, which is 3. So final answer for this question will be 3. Okay, order with respect to NO will be 2, order with respect to hydrogen will be 1, overall order of the reaction will be 2 plus 1, 3. Yes. So there is some kinetics. Yeah. Now finding the rate law of a complex reaction, right. So there is an application of rate law. Now another one was from organic. Okay, so that is from carbonyl section. Complete reaction of acetaldehyde is done with formaldehyde. Okay, and the reagent was NaOH, and it gave finally P and Q. P does not give tolerance test, Q after acidification gives tolerance test. Okay, so let's find P and Q first. The famous reaction of acetaldehyde with formaldehyde, you know, those are aldol reactions, and finally since we are heating with constant NaOH, it can undergo Cannizzaro reaction also. So let's start with the reaction. CH3 CHO was given to us initially, and formaldehyde, okay, in alkaline medium. You know, aldol reaction occurs. So aldol reaction occurs. First alpha hydrogen will be replaced with HCH. Okay, so it is an addition reaction. CH2 CHO. This alpha is going to attack on that carbonyl, right? That is an aldol reaction. And formaldehyde now becomes CH2OH. Now, again, since we are using excess of formaldehyde, again the reaction goes forward. One more aldol can occur because still alpha hydrogens are remaining in acetaldehyde part. So next equivalent of HCHO also reacts in basic medium, and we will get one more CH2OH unit on the alpha carbon after aldol addition reaction. Okay. Now we have again HCHO present in the medium. So one more aldol reaction can occur because we are remaining with one more alpha hydrogen. So one more aldol addition occurs in the same medium, giving rise to CH2OH thrice, right? CH2OH thrice, CH. So it is a final aldol product. Now again we are heating with constant NaOH. Now you know no more alpha hydrogens are remaining on this carbon. So on heating with HCHO in presence of OH minus, now Cannizzaro reaction can work. Okay. So it was 3 aldols and one more Cannizzaro reaction. So this will give rise to, you know, who is hydride donor in this case? In this case, HCHO will act as a hydride donor, okay? Because, you know, HCHO is more electrophilic, so a more amount of this species will be present in the medium, and therefore this will be present in, since this is present in greater concentration, that will be the better hydride donor. You know, hydride transfer is the rate determining step for Cannizzaro reaction. So always formaldehyde will donate its hydride group to the other partner. So that will happen onto this carbonyl group. Okay, this is a aldehyde not having any alpha hydrogen. So that will be getting reduced and formaldehyde will be oxidized to formic acid or formate. Okay, so the product, one of the product will be this particular alcohol, which is a reduction product. CHO group is reduced to CH2OH. Okay, so C surrounded by 4 CH2OH groups. Now the oxidized product will be formate. H, one more hydrogen is remaining over there, so HC double bond O minus Na plus, sodium formate. Sodium formate will be the other product. Now let's find who is tolerance positive, who is tolerance negative. Okay, clearly this is a tolerance negative. This will not be giving a tolerance test, and that on acidification, you know, on acidification it will be becoming formic acid, which looks like an aldehyde, therefore tolerance positive. Okay, so we got P and Q. Let's assign the correct name. P is tolerance negative, Q is tolerance positive. So this is P, that is Q. Right. Now what they are doing with, they are continuing with P. Okay. So this is their favorite product. So they took P again and treated with excess of cyclohexanone. Okay. In presence of catalytic amount of para-toluene sulfonic acid. Okay. Catalytic amount of H plus acid. Catalytic amount of acid they are using. And that gave final product R. So question is about R. So let's first find out what is R. So we are taking this alcohol P. P has 4 hydroxyl groups and treating it with cyclohexanone. So let's see what first equivalent of cyclohexanone does on P. You know, alcohol and ketone or aldehyde, they are compatible. They can do nucleophilic addition reaction and followed by substitution also, right? Elimination, followed by elimination. So this will be first giving us a hemiketal and finally a ketal, and that will be a cyclic ketal because this is like acting like a diol. Okay, first this part attacks, creating an OH group over there and OR group over there. OR is nothing but this one, that is a hemiketal. Now this OH group is again removed in presence of acid, of course. Okay, this reaction will happen in presence of acid catalyst only. What is the role of acid catalyst? That will just activate the carbonyl group towards nucleophilic addition. This is a weak nucleophile. Okay. So that reaction is promoted by the use of para-toluene sulfonic acid, which is nothing but a H plus donor. So that reaction occurs. Again, one more reaction occurs that leads to H2O removal, and we'll be getting a cyclic ketal like this, or CH2, right? This is the product, CH2OH, CH2OH. And they have clearly mentioned that they are using excess of cyclohexanone. So more amount of cyclohexanone is available in the medium compared to P. So again this can, this is again going to act as a diol, like ethylene glycol, just that we have one more intermediate carbon present in that. Okay, so that part will again act as a diol, and it can again lead to a ketal formation. Okay, so let's take second equivalent of cyclohexanone and do the addition elimination reaction once again in presence of H plus. So that will give us one more cyclization. Okay, and the product will be looking like, okay, let's draw the below portion first, and now the other portion, the new one, right? CH2O that clubbed with cyclohexanone ring. Okay, yes. So that is the final structure we are getting after this addition elimination reaction series, right? So in presence of excess of cyclohexanone, we are going to get such a cyclized ketal product. That is what is called as R in the question. So we identified R, we can see methylene groups, we can see oxygen atoms also in R. So let's take a total count of methylene groups and oxygen atoms. So methylene groups, if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 methylene groups plus oxygen atoms 1, 2, 3, 4, right? So 1, 2, 3, 4, 4 oxygens. That makes total 18. So total count of methylene groups and oxygen atoms in the final product R is going to be 18. So our answer will be therefore 18. Right? So 18 is the answer for question number 10. Yeah, that is from carbonyl chemistry, nucleophilic addition elimination reactions of ketones, ketal formation. Now, going to the next one, we are given with certain compounds. We are asked to find out total number of isoelectronic species, isoelectronic with NiCO4. Okay, isoelectronic species, it's a strict definition if you follow that says that species, two or more species containing same number of valence electrons. Okay, we just need to look into valence electrons only. Same number of valence electrons, same number of atoms, and same structure also. Those are called as isoelectronic. That is a very strict definition of isoelectronic species, right? So if we follow that particular strict definition of isoelectronic species, since they are using this term isoelectronic, if you are following the strict definition of isoelectronic species, we will be getting only one isoelectronic species from this set. NiCO4, if you are focusing on central metal nickel and taking a total valence electron count of nickel, its atomic number is 28 and 4 carbonyls are coordinating to it. So nickel has 10 valence electron before bonding plus 2 lone pairs. 1 lone pair is donated by each carbonyl, right? So 8. That makes 18 valence electron around nickel, and nickel is bonded to 4 carbonyl groups. And if you look into this complex, their Cr4 minus is the central atom, Cr4 minus. Cr4 minus again has 10 valence electron. Chromium had 6 valence electron, and 4 minus is its now. Okay, 4 minus means 6 plus 4, 10. 10 plus 2 into 4, 8, which is 18 electron. So if you are strictly following the definition of isoelectronic species, our answer will be 1. Or if you are simply calculating or taking a total valence electron count around the central metal, then of course you can find more number of complexes. This will be having same number of valence electrons around iron, okay, after bonding. This also will be having same number of valence electrons around cobalt after bonding, okay. So that depends on the definitions, right? So yeah, so strictly speaking, NiCO4 is isoelectronic with CrCO4 4-. Okay, so that was one question from coordination compounds, the electronic structure of coordination compounds, right? Yeah. So let's move on to the next question, that is from organic again. Okay, a large organic compound, a chain organic compound is given to us and it's applied on a series of reactions. Let's see what is the final product P for this series of reaction. Okay, this is an alkyne, a terminal alkyne. Alkyne is treated with Hg2 plus and acid solution. You know, it is a hydration reagent for alkynes. And it is a Markovnikov addition also. Markovnikov addition will give us to a stable enol formation, more stable enol product first, and then it will be giving us, right, first we will get a enol formation, and after that it tautomerizes quickly to keto form, okay, keto form, not the aldehyde, major product will be ketone. So that is why we call it Markovnikov addition of H2O on alkynes. So final product will be CH3 of the first step only, okay, CO, then 15 times methylene groups, COOET. Now after that we are doing a Clemmensen reduction, zinc amalgam and HCl, right? Clemmensen reduction we are doing, keto group will be reduced to methylene group, okay. So we will be getting a hydrocarbon over this region. So after second step we will be getting CH3, CH2 16 times, right. So this will be now 16, previously it was 15, this also becomes CH2. So that is our next product after Clemmensen reduction, right. Of course, for clarity they have given H3O plus also, so that make sure that ester is hydrolyzed to acid. So at the end final product P will be CH3 16 times CH2 COOH, final hydrolyzed product. So that is called as P in the question. This can be written in short like this, C17 H35 COOH, which makes it familiar to you, right? That is stearic acid, long chain fatty acid. C17, 16 plus 1, 17, and 32 hydrogen plus 3 hydrogen, 35, and then 1 COOH group. That is a stearic acid. So P was stearic acid. Now after that they are continuing with the reaction. P is then treated with glycerol in presence of acid catalyst. You know, P is a carboxylic acid according to function group. Carboxylic acid is treated with glycerol, which is an alcohol. You know that glyceryl ester will form, glyceryl ester of stearic acid will form. So let's see what is the structure of that one. Glycerol, you know, it is a propyne 1,2,3 triol, right? So that OH, yes, with excess P, they are taking C17 H35 COOH in excess amounts. So all the 3 hydroxyl group can get esterified with that particular acid, okay. Yes, so the glyceryl ester, which is called as Q, so the structure of Q, you know, it is done in presence of acid catalyst, esterification reaction it is. So that esterification will give us glyceryl ester of stearic acid with the loss of 3H2O. Now, now we got Q, that is Q. So this glyceryl ester Q is then treated with aqueous NaOH excess. Okay, so let's see what is the product after treating with NaOH. Excess of NaOH they are using. So this ester simply hydrolyzes back right to the alcohol, and since we are using alkaline medium, carboxylate salt, which is the soap, right, sodium carboxylate. So this is a base catalyst hydrolysis reaction only. So hydrolysis will give us alcohol again, OH plus, yes, 3 C17H35 COONA. Okay, that is nothing but sodium stearate, common soap. So this reaction was called as saponification, if you remember from chemistry in everyday life chapter, or this is a very familiar reaction also, you know, saponification reaction, right. So NaOH, that is lye. So lye, after treating glyceryl ester of stearic acid with this lye, we will get sodium stearate soap. Now what they are doing is, they are treating again this with calcium chloride, and they get a compound R, which is a calcium soap. Okay, so on treating with this with calcium chloride, you know, there is a hard water. You know, this does not work in hard water due to a complex formation, and that complex is called as R. So calcium stearate is formed. Sodium stearate switches to calcium stearate with the removal of NaCl. So that becomes 3/2 Ca C17H35 COO twice, which is a precipitate. So that was soluble, this is a precipitate. Okay, that is the reason for hardness, right. Yes, not working of soap in hard water. So that is our final product called as R. Yes. Now let's again go back to the question what they want. Yes, starting with 1 mole of Q. Okay, so 1 mole of Q they want to start with. From 1 mole of Q, what is the amount of R produced in grams? Okay, from 1 mole of Q, yes, from 1 mole of Q, you know that 3 moles of sodium soap will be produced. Okay, all these 3 C7H35 units will be converted to 3 moles of soap. And now on treating this with calcium chloride, you know, 3/2 moles of this will be forming, right. 3/2 into 2, overall 3 moles of stearate we have to have in the final solution also. So 1 mole, you can say 1 mole of Q effectively gives 3/2 moles of R. So 1 mole of Q is going to give us 3/2 mole of R. We want the mass of R produced. So we just need to find out molar mass of this particular unit and multiply it by 3/2. Molar mass of R is found to be, right, you can just add it, everything is given in the hint section. So that will give us 606 grams per mole as the molar mass of R. Now that multiplied by 3/2, that will be 909. So 909 grams of calcium stearate precipitate will be formed. So we can enter our final answer as 909. Okay, in grams. So that was again from organic reactions only, but clubbed with chemistry in everyday life chapter, the soap section. So previously we had a question related to artificial sweetener, which was again from that particular chapter, chemistry in everyday life. Yes, so that was another numerical question. So the final answer we can enter 909. And now let's see one more numerical question we have in this particular third section. So that was again from coordination compounds. Among the following total number of diamagnetic complexes we need to find out. Okay, so let's easily check how many diamagnetics are present here. MnNH36 3 plus, Mn3 plus it is, Mn3 plus is D4 configuration, D4 octahedral it is, D4 octahedral will never be diamagnetic species, right? either in low spin state or in high spin state. That will be paramagnetic only. So no need to worry about this. This is always paramagnetic. MnCl6 3 minus again Mn3 plus. So that is also going to be paramagnetic. Okay, Mn3 plus, it is D4 paramagnetic. So D4 octahedral will always be paramagnetic. Now FeF6 3 minus, that has Fe3 plus as a central species, Fe3 plus. Fe3 plus has D5 electrons, right, odd electrons, which is again paramagnetic. Now if you look into next one, cobalt 3 plus is the central metal. Cobalt 3 plus, it has D6 configuration. Okay, that depends on inner orbital or outer orbital nature of the complex. So here the ligand is weak fluoride ion only. So fluoride ion will not force pairing of the 6 electrons of cobalt 3 plus. Therefore this will remain as high spin complex and it will be paramagnetic. Okay, 4 unpaired electrons we can have in that complex on central metal. Now FeNH36 3 plus, Fe3 plus again, which is D5 odd electrons. So paramagnetic it will always be. Now COEN thrice 3 plus, okay, only one is remaining. Let's check if that is diamagnetic or not. Cobalt 3 plus it is, which is D6 configuration, and you know En, ethylene diamine, is considerably strong ligand. Therefore it will force pairing of the electrons and it will have ultimately T2G6 configuration, T2G6 non-paired electron. So that will be diamagnetic species. So out of these complexes only the final one is diamagnetic. So our answer will be 1. Okay, now let's see what we have next. That is the next section. Next section is matching type. Okay, match the following type questions. We have 4 such questions. First one was related to practical chemistry, right, and clubbed with electrochemistry or equilibrium chapter, we can say. Okay, practical always will have connection with a lot of chapters. Let's see, in a conductometric titration, small volume of titrant is added stepwise to a large volume of titrate. Okay, they are clearly mentioning that a titrant has high concentration and it's added drop wise, and titrate, okay, so titrate we have in the beaker and we are adding titrant into it. Very well explained question is, so no confusions regarding that part. So titrate we have down, titrant we are adding from up. Now, and the conductance is measured after each drop addition. So limiting molar conductivity of ions are given to us. Okay, Ag plus, K plus, several ions have been mentioned. Their limiting molar conductivity value. Limiting molar conductivity we can use because you know the solution is of much lower concentration, so that will give a rough idea about the conductance values of the ions involved in the titrate mixture. Yeah, so so that is given. So informations are clear. Now for different combinations of titrants and titrates given in list 1, match the correct conductance versus volume of titrant plots. So let's see the first case. AgNO3 is being added to KCl. Okay, titrate is KCl, and into that we are adding AgNO3, right? So ACl, into that AgNO3 is added. So we have a dilute solution of KCl. Okay, a dilute solution of KCl. Into that drops of AgNO3 solution are added. Now let's see what reaction is happening in the mixture. So KCl is getting AgNO3 from above. You know, precipitation reaction occur. AgCl precipitate forms. That does not contribute to conductivity of or conductance of the solution. Okay, that will remain as a solid. Now AgCl precipitates. Now after that KNO3 is also produced, which remains in the solution in the ionic form, right? K plus ions solvated, NO3 minus ions solvated. So previously, before addition of AgNO3, we had K plus ions and Cl minus ions solvated individually, and now with each drop of AgNO3, gradually KCl is being replaced with KNO3, right? So if you correctly look into the solution, each KCl is gradually changing to KNO3. Okay, AgNO3 changes to AgCl, which does not come into picture, that is a precipitate. So KCl is being replaced with KNO3. So number of K plus ions remains the same. Then what is varying? Total number of ions is also remaining almost the same, because each KCl is replaced with KNO3, right? Then the only difference is chloride ion is replaced with NO3 minus ion. So if we had initially 10 moles of KCl, now 1 mole of KCl got reacted. Now in that 1 mole place, we have 1 mole KNO3 and remaining 9 mole KCl. Okay, 9 mole KCl plus 1 mole KNO3 will be the situation then, right? So that way, simply speaking, each chloride is replaced with nitrate ion gradually in this process. Okay, so as volume of titrant is increased, chloride ion number decreases and nitrate number increases. So total number of ions remains the same. Okay, so you know, Cl minus is replaced with NO3 minus, and if you look into the table, NO3 minus's conductance is little lower than chloride's conductance. Okay, so effectively we will be seeing a slight decrease in the conductance of the solution, right? Because Cl minus goes to precipitate, and in that place NO3 minus we are getting, overall number is not changing till equivalence point. After equivalence point, you know, in all these cases total number of ions increases, except in last case. There we are adding acetic acid, which is a weak electrolyte. In all other 3 cases, we are adding strong electrolytes. Okay, so strong electrolytes, after 100% reaction, whatever is happening in the mixture, then afterwards their conductance will increase steeply because total number of ions increases, right? That is what you are seeing in all the graphs, right? After equivalence point, there is an increase in conductance. Before that, what happens? That is the main focus of this question. So let's see. In this case, Cl is replaced with NO3 minus. Therefore, we expect a slight decrease in the conductance of the solution. So we can match this. Okay, we may match this with 3. There is a slight decrease. Okay, we are sure that there is a decrease because NO3 minus is coming in place of Cl minus, and NO3 minus has slightly lower value of conductance. And we have 2 such graphs. Okay, 2 or 3, right? In 2 also it's decreasing first, in 3 also it's decreasing first, in 2 steep decrease happens, in 3 slight decrease happens. So there is a confusion, right? So let's go ahead and solve that confusion. In second case, we are adding KCl into AgNO3, same reaction but in the reverse order. Okay, so we are taking AgNO3 containing solution in which Ag plus ions and NO3 minus ions are free to move, and into that KCl is being added. Okay, so with each KCl addition, same reaction occurs, KCl plus AgNO3 giving rise to AgCl precipitate, which does not comes to conductance measurement, and finally KNO3 also, which stays in the solution. Okay, so in this case we are measuring conductance of this particular solution only. Okay, so that solution's conductance, if you measure, what difference is happening in the solution part, each AgNO3 with addition of KCl, gradually each AgNO3 in the solution is replaced with KNO3. AgCl will go to precipitate, right? So AgNO3 is replaced with KNO3, or simply speaking, nitrate ion is not changing. Their number is not changing with time, but Ag plus is being just replaced with K plus. Okay, whatever Ag plus we had previously, those are gradually replaced with KNO3. Total number is also not changing. Total number is not changing in this case also. Total number of ions up till equivalence point. So don't worry about total number of ions. The only factor is change in nature of ion. Okay, Ag plus is replaced with K plus now in the solution. And clearly, if you look into the table, K plus has a higher conductivity than Ag plus. Okay, K plus has higher conductivity. Previously, we were replacing chloride with nitrate. Then nitrate had a lower conductivity than the previous chloride. That is why the slight decrease happened. So here we are replacing Ag plus with K plus. So K plus has higher conductance. So we expect an increase, slight increase in the conductance value of the solution. So Okay. So we can expect slight increase in conductance value, which is mentioned in fourth graph. Okay. So we would match Q with 4. Okay. So we have yes, we have only one graph which shows a slight increase from initial point onwards. Okay. The first graph is a little different. You can see first a little drop in conductance, then an increase in conductance. So that is a different thing. Right? That happens if titrant has weak electrolyte initially. Okay, that happens if you, let's say, if you take acetic acid initially and into that some strong bases are added. Okay, so initially there is a slight decrease happening because H plus ion is replaced with some other cations, and followed by increase in conductance because number of ions is increasing now, because in original acetic acid solution there were a little number of ions only, acetic acid being a weak electrolyte. So now with continuing the experiment, as we continue with the experiment, more number of ions will be present before reaching the equivalence point itself. So due to increase in number of ions, then it increases. Okay, so that is a different case when we have weak electrolyte in the solution, the original solution. Okay, so no need of confusion with that graph. Yes, so P3Q4, our answer is almost fixed. Okay, but we need to cross check everything. Yeah. So next one are NaOH and HCl, right? So we are taking initially NaOH solution, NaOH in the beaker and adding HCl dropwise, right? The reaction, neutralization reaction happens. NaOH plus HCl will give us NaCl plus H2O. H2O is solvent molecule. So what change is happening initially? NaOH present in the medium is converted to NaCl. Effectively, OH minus ions are replaced with chloride ions. Okay, so total number of ions is not varying with time. Okay, before I am talking about before equivalence point portion only. So before reaching equivalence point, in all the first three cases, no change in total number of ions is occurring. So just replacement of one type of ion with one anion with another anion happens here. OH minus is replaced with chloride ion. Now let's look at chloride's relative conductance. So from the graph it is clear that chloride has very low conductance with respect to OH minus. OH minus has almost 20 units of molar conductivity and chloride has only 7.6, below half of that. So we will expect a sudden decrease or steep decrease in the conductance value before reaching equivalence point, right? So that particular graph is option 2. Okay, so R is going to match with 2. Now that is also matching, right? Now we have to verify last case also. Okay, in there we have NaOH present in the, right? NaOH present in the beaker, and titrant is acetic acid. We are adding acetic acid into it. So on adding CH3COH, again neutralization reaction occurs, like in the case of that. But that case both were strong, right? This case adding we are adding a weak acid only. Anyway, reaction occurs. NaOH is present in the medium, CH3COH is added dropwise. So neutralization happens, we will get salt, sodium acetate and H2O. Okay, this time also number of ions is not changing up to equivalence point. Okay, total number of, NaOH is present as Na plus and OH minus ions. Now in place of NaOH, gradually we are having CH3CO Na produced, right? So effective change occurring in this case is simply replacement of OH minus ions with CH3CO minus ions, right? OH minus is gradually replaced with acetate ion. Okay, one anion is replaced with other anion. So in that case, what happens, if you refer to the table, we have every information given to us, so that is very straightforward therefore. So this is simply analytical question. OH minus has very large conductivity with respect to acetate also. Okay, among cations, H plus has very large conductivity. Among anions, OH minus has very large conductivity. So if you are replacing OH minus with acetate, definitely there will be a steep decrease happening in the conductance value. Okay, that is happening in case 5. Okay, that is happening in case 5. And you can see after that there is a slight increase only. Okay, or almost no variation in the conductance value after equivalence point. So after equivalence point means all the NaOH are neutralized to sodium acetate and H2O, and after that what is happening on addition of acetic acid, just that amount of acetic acid in the solution increases, right? Acetic acid unit is a weak electrolyte. So weak electrolyte is not going to produce much ions in the solution. So there is not much variation occurring in the conductance value after equivalence point in the case of acetic acid addition. In the case of acetic acid addition, if you are adding HCl, if you are adding NaCl, if you are adding some other strong electrolyte, they will produce more and more ions. All the added molecules will dissociate into ions. So definitely conductivity values or conductance values will be increasing if we are adding strong electrolyte into some reaction mixture. But in this case we are adding weak electrolyte, therefore conductance is not varying much. So that is our simple answer. Option C will be our answer here. So it was purely an analytical question asked from practical chemistry branch. You can of course have a connection between the electrochemistry also. Yes. Now next one we have another from chemical bonding. We are given with certain xenon compounds. We are asked to find out the electron pair geometry around xenon and lone pairs on xenon. Okay, lone pairs on xenon only. So XeF2. If you draw the Lewis structure, xenon had 8 valence electrons. Now you can see 1, 2, 3, 4, 5, 6, 7, 8. That is the correct Lewis structure of XeF2. Now if you count the total number of lone pairs on xenon, you will find it is 3 lone pairs of electrons with trigonal bipyramidal geometry, right? Trigonal bipyramidal geometry. So P is matching with 5. Okay, P is matching with 5. Then let's look into Q. XeF4 is Q. So structure of XeF4, if you draw, it is having 2 lone pairs on the xenon center, and it has an octahedral electron pair geometry. Octahedral electron pair geometry with 2 lone pairs of electron on xenon. That will be option 3. So there itself our answer is ready. P5 and Q3, right? Option B. Now let's verify with other options also. Are XeO3, it is XeO3 structure. Okay, 1, 2, 3, 4, 5, 6, 7, 8. That is the structure of XeO3. 1 lone pair, tetrahedral geometry of electron pairs around xenon. So R is matching with 2. Okay, we are correct. XeO3F2. If you draw the structure of XeO3F2, again we will find that fluorines go to the axial positions and oxygens will be on the equatorials. So that will make a trigonal bipyramidal geometry with no lone pair on xenon, right? 1, 2, 3, 4, 5, 6, 7, 8. So 0 formal charge, that is a stable structure. No lone pair on xenon. So trigonal bipyramidal geometry with no lone pair of electrons, that is 4. So B is our exclusive answer. Okay, so that was one question from chemical bonding again. Okay, now the third matrix match type questions, match the following type question. That is from organic. Third and fourth, they are from organic chemistry. Let's see. Alkenes are given. Okay, alkenes are given, and some may contain carbonyl group also, and we are doing certain reaction. Finally, we are getting alcohols. Okay, so let's see. First reaction, ozonolysis of cyclohexene. Cyclohexene is ozonolized. Cyclohexane is transforming to hexane 1,6-diol, right? So that diol is produced, then it is treated with aqueous NaOH and heated. Aldol condensation occurs. Aldol addition happens from this particular alpha carbon to that carbonyl, creating a 5-membered ring structure and a CH group outside. There is an aldol. Okay, OH, of course, there is an aldol. Heating is also mentioned. So heating will cause elimination of water from the structure, giving rise to aldol condensation product. Okay, so that alkene is finally converted to an alpha beta unsaturated carbonyl compound. Right. So that is what happened in first two series of reaction, right? First two stages of this reaction. Now this is treated with ethylene glycol in presence of PTSA. PTSA is also already defined in this question paper, para-toluene sulfonic acid, that is just acting as an H plus donor. Okay. Ethylene glycol, PTSA is used. You know, carbonyl group is protected in the form of a cyclic acetal, right? So let's see why they are doing this. So CHO is converted to cyclic acetal, okay, cyclic acetal form. Yeah, so that is the product after step 3. Ethylene glycol PTSA will give us 5-membered cyclic compound like this. And now we are performing hydroboration oxidation. On this hydroboration, you know, antimark adhesion of H2O is happening, and therefore CHO is forming, and here OH group is attached. Okay, H and OH are added in antimark fashion, and after that we are doing H3O plus. Okay, if we are applying acidic solution into acetal, that will hydrolyze and we will get back the original aldehyde unit. Okay, so OH CHO is produced, which is then treated with NaBH4. So reduction occurs, reduction gives OH CH2 OH, right? That is produced. So that particular alcohol is the final product of first reaction, and that is this one, right? So P is matching with 3, P is matched with 3 in all the 3 options, right? Now let's go to the another reaction also, Q. Okay, Q, yes, again similar series of reactions are performed. So 1-methyl cyclohexene is Q. 1-methyl cyclohexene is first transformed to corresponding carbonyl compound in the reductive ozonolysis step. Okay, that is formed. Now secondly, they are doing aldol condensation. So aldol condensation will give us that particular alpha beta unsaturated carbonyl compound, and after that ethylene glycol is applied for protection of ketone group. So that will give us, okay, that particular cyclic acetal, and then we are doing hydroboration oxidation. So hydroboration oxidation will give antimarconic of alcohol, okay, and then that acetal is not affected, you know, and followed by hydrolysis. So this is not an acetal now, this is a ketal. Yes, so this ketal is converted to ketone, okay, like this, and then we are applying sodium borohydride. Sodium borohydride will give a reduction of ketonic group, secondary alcohol is produced. Okay, so that is a final product, and that product we can see in option in compound 5. This is the one, right? So Q is matching with 5. So Q is matched with 5 in 2 options. So Q is matched with 5 in 2 of the options. Now let's go ahead whether R is matched with R can be matched with 1 or 4. Okay, so R is this particular compound which has a ketonic group in the initial step itself. So we are doing ethylene glycol H plus reaction on this particular ketone, and that will, you know, convert to cyclic ketal, right? Followed by oxymercuration we are doing, right? Oxymercuration, demercuration. Mercuric acetate followed by sodium borohydride is done. So in that step we will be getting a Markovnikov addition of water on this alkene. Okay, so CH3 OH is formed, Markovnikov alcohol is produced. That is a final product. And now we are doing a hydrolysis of this compound. Hydrolysis of this will give us the ketone group back, right? So ketone is regenerated, CH3 OH, and then NaBH4 is applied. You know, ketone is converted to secondary alcohol, OH, CH3, right? So that is the final structure. So that is, let's identify that structure. This is going to be 4 or 1, that is going to be 4. So R is matched with 4. R can be matched with 4. So option A would be our answer. Let's check, let's verify. The case of S also, S is treated with ethylene glycol. S is treated with ethylene glycol. You know, cyclic ketone is produced again. Right? CH3 is there. Then we are doing antimark addition, hydroboration oxidation reaction. So cyclic ketone is formed, and there, yes, antimark addition, hydroboration oxidation it is. After that, hydrolysis is performed. Hydrolysis will give back the ketonic group CO, CH3, OH, and then sodium borohydride is applied. Sodium borohydride will give us secondary alcohol. Okay. So this particular diol is the final product of S, reaction S. Okay, so that is clearly 1. Okay, compound 1 it is. So S is matched with 1. So option 1 is going to be our answer. Option A is going to be our answer. Now we have one more question of this form. Match the following type. Here we have again organic reactions given in list 1 and final products given in list 2. In this case, these are aromatic compounds. That is the only difference. Okay, let's see. They are short reactions. Benzene sulfonic acid treated with molten NaOH followed by H3O plus. You know, it's a preparation of phenol. Phenol is produced, and followed by constant HNO3. Constant HNO3, you know, phenol, constant HNO3. If you treat, the aromatic product will be picric acid. Okay, picric acid, polynitration occurs, and you can see picric acid over here. Okay, so P is matched with 3. P can be matched with 3. Now after that, let's see second reaction also. Nitrobenzene is treated with constant HNO3. Constant HNO3, if you treat, nitration happens at meta position because NO2 is meta-directing group in electrophilic substitution reaction, followed by tin HCl reduction. You know, amines are produced, primary amines are produced, NH2, 2 NH2 groups are produced, and after that diazotization is done. Both the amino group convert to diazonium group into plus Cl minus, and after that it is treated with H2O at normal conditions. You know, that is a preparation of phenol. Hydrolysis will give us phenol. 2 OH groups will be present. Okay, so after that we are again doing nitration of the final compound. Okay, constant HNO3 is applied. Nitration, you know, of this compound will give us introduction of NO2 group at ortho and para positions. These are the ortho and para positions. So we can expect entry of 3 NO2 groups at those specific sites. This is the expected product of the series. So that product, where is the product present in the list 2? Let's check. This is option compound 5, right? Compound 5. So Q is matching with 5. Q is matching with 5. P matched with 3. Q matched with 5. So of course our answer would be option C, right? So let's check. Let's verify with the other reactions also. So OH, this compound is treated with constant H2SO4. You know, sulfonation occurs. We can expect sulfonation at 2 locations, at this site and that site preferentially, right? Yeah, that is a preferred site of sulfonation. Now after that, nitration is done. On nitration of this particular sulfonated phenol, one more location is free here. That location will be nitrated. Okay, so this is a trick for controlled nitration of phenolic compounds. First sulfonate it, then it is slightly deactivated, then do or masked at the reactive sites, and then if you do nitration, yeah, you can lower the number of nitro group entering into the ring. Now after that, we are heating this with acid solution. Heating this with acid solution will remove the sulfonic acid groups. Urasulfonation is reversible. So on heating with acid, okay, those groups will be removed and we'll get that particular nitro compound. Okay, so that let's identify from the options, that is 4. Okay, this compound is 4th one, so R is matching with 4, which is mentioned in the option C. Now S is going to match with 1. Okay, S is going to match with 1. Let's quickly verify. Toluene is oxidized first to benzoic acid, and in second step nitration is done. Okay, severe nitration is done. Let's look at option 1 also, compound 1 also. Compound 1, you can see 2 nitro groups, right? 2 nitro groups. So let's add 2 nitro groups. That means let's nitrate it at both the meta positions. Okay, that particular compound is formed by exhaustive nitration, and after that thionyl chloride ammonia reaction is done. You know, carboxylic acid changes to carbonyl chloride. Okay, acid chloride is formed first. After that, on treating with ammonia, nucleophilic addition elimination reaction occurs, so that will give us CONH2 amide. Okay, amide is produced. CONH2 is then undergoing Hofmann-Bromide reaction, Hofmann-Bromide degradation reaction, right? So on Hofmann-Bromide degradation reaction, you know that converts to aromatic primary amine. Okay, that is formed, and after that diazotization done. Diazotization creates a diazo group over there. 2 nitro will be present here as such, followed by hydrolysis of diazonium salt. Hydrolysis will give us 1 OH group and 2 nitro is already present over there, that is produced, right? So that compound is 1. Okay, that is. So that was the last question. Yes, 17th question. We had overall 17 questions. This is the last question of our JEE Advanced paper 1 chemistry this time. Okay, so hope you could solve correctly most of the questions well in the limited period of time available for you. Okay, hope you enjoyed the questions and thank you all the best.